Okay guys, so here is the review guide key. Some of it I'm going to talk through, some of it I will actually do the problems. So for number one, what's the difference between a solvent and a solute? The solvent is the substance that is doing the dissolving, whereas the solute is the substance being dissolved. Together they make a solution, by the way. Number two, what is an electrolyte? Electrolyte is something that has the ability to conduct electricity, and it asks how you can differentiate between strong, a weak, and a non-electrolyte. So if you remember, our strong electrolytes are any ionic, soluble ionic compound placed in water, any strong acid, or any strong base placed in water are all strong electrolytes. Weak electrolytes are weak acids and weak base solutions, and non-electrolytes are solutions of covalent compounds. So you could give examples that fall into those categories. If you don't remember that very well, there is a lesson on that on the website still, so you're welcome to take another peek at that. Next question, which of the following copper 2 salts are soluble and which can you not determine based on your limited knowledge of solubility rules? So you should have said that CuNO32 and CuC2H3O22 are both soluble, so copper 2 nitrate and copper 2 acetate. And then the other three are unable to be determined because the four substances that we know, ions that we know will always make things soluble, are nitrate, acetate, ammonium, and our alkali metals. Number 4 says, which contains a greater mass of solute? So with this one, there's a couple of ways to go about doing the problem, but probably I would think most of you will actually just calculate it. So let's go ahead and do that. So we know the molarity. So you know you're going to use molarity equals moles over liters. So the molarity of the NaCl, start with that one, is 0.1. And we don't know the moles, but we do know the volume is 1 liter. So when you multiply that out, you know that you have 0.1 moles of NaCl. You can convert that into grams. So for every 1 mole, NaCl is 58.5 grams. So that means you have a total of 5.85 grams for the NaCl one. Then for the other one, which was Na2CO3, you know the molarity is 0.06. Don't know moles, you know the liters. Notice the nice easy numbers for you. So 0.06 moles of Na2CO3. And the molar mass is 106.0 grams for every 1 mole. So when you multiply that one out, you get 6.36 grams. It asked us which one had more grams, so your answer would have been that one. Okay. Number 5 says you have a bottle of solid Na2CO3 and need to make a 500 milliliter solution that's 0.2 molar. It wants us to explain the process. So for number 5, first thing we got to do is some math. We're going to always write our equation first. So the molarity we're trying to get to is 0.2. We don't know how many moles we have, but we know we have 500 milliliters, which is 0.5 liters. Now if I cross multiply that, I will get that I have 0.1 moles. So we're going to multiply for every 1 mole, it's 106.0 grams. And if I multiply that and sig figs, what do we got for sig figs? 2. So it rounds to 11 grams of Na2CO3. Now the problem said to explain the process, so you should have the following. You should have told them to obtain a 500 milliliter volumetric flask, place 11 grams of Na2CO3 in the flask, fill it halfway full with distilled water, swirl until the solid is dissolved, fill to just before the fill line with distilled water, and then use a pipette to pipette in the last of the distilled water to get the meniscus lined up perfectly with the fill line. Cap it and invert it. And that should cover that question. All right, next one says, which has a higher concentration of hydrogen ions? So we're going to have to figure out how many hydrogen ions are in each situation. So the first one is telling you that you have HCl and that its concentration is 0.15. Well, we know HCl is a strong acid, so it's going to break up into H plus and Cl minus. H plus's concentration, therefore, since it has a 1-to-1 ratio, must be also 0.015. For the other solution, they told us the pH of it. And we know that pH is the negative log of 1, oh, not bad. pH is the negative log of H plus. And they told us the pH was 1.2. So that'll be the negative log of H plus. We move the negative sign over to the other side. And then we're going to take the inverse log, which is simply just hitting the second button on your calculator and then the log button. Same thing on my calculators that you'll be using. And take the negative or second log of negative 1.2, and you will end up finding out that the concentration of H plus in this situation is 0.063. So you're comparing 0.015 with 0.063. So this is clearly the higher concentration of H plus. So for number 7, they asked us what is the equivalence point in a titration. The equivalence point in a titration is the point where all the acid and base have neutralized each other. What is the end point in a titration? That's where the color change occurs. And it says, what is the function of an indicator in a titration? Well, as long as you've picked the appropriate indicator, your end point and your equivalence point should happen with the same drop of fluid. So it's the purpose of the indicator is to indicate that the equivalence point has been met. But you obviously have to pick the right one in order for that to happen. All right, so on to number 8. Start 8 here. So for 8A, you have been given nickel 2 chloride reacting with ammonium sulfide. Notice it says solution for both of them. So that's going to be NiCl2, and that's aqueous because they told us it's a solution, reacting with NH42S. Here's where naming is going to be very important. Now, we do a double replacement reaction and crisscross our charges. We'll end up with NiS, which is a solid, and then 2 NH4Cls. I balanced that as I was writing it, but you might have done it first and then come back and balanced it. So that's the molecular equation. Now, I knew that this one was a solid and that this one was aqueous, mostly because of this one being aqueous. I knew ammonium was aqueous, therefore the other one has to have been solid. So I'm going to take my aqueous ones and I'm going to dissociate them. So we'll get Ni plus 2 plus 2 Cl minuses plus 2 NH4 pluses and then S minus 2. And then on the other side, I'm going to leave NiS alone. And then I'm going to have 2 NH4 pluses and 2 Cl minuses. So in terms of canceling, ammoniums cancel, chlorides cancel, and I end up with Ni plus 2 plus S minus 2 yields NiS. And that'll be my net ionic equation. Now time for 8B. Now 8B says magnesium to nitrate solution reacts with sodium phosphate solution. So that is going to look like this. We will have MnNO32, and that's reacting with Na3PO4 to make Mn3, I need a parenthesis, PO42 plus NaNO3. And we need to balance that. You might need to do the math wave for this one. You get a 3, a 2, a 1, and a 6. Now, in terms of phases, they already told us these ones were aqueous. Mn3PO42, nothing stands out to me, but if I look at the other product, I see, well, 2 different things that tell me it's always soluble. So I know that one's aqueous, therefore this one must be a solid if this is a precipitation reaction. So now I'm going to dissociate. So I'm going to get 3 Mn plus 2s plus 6 nitrates plus 6 sodium ions plus 2 phosphates. And then I leave this guy alone. And 6 sodiums, ions, and 6 nitrates. So that makes my nitrates cancel. That makes my sodium ions cancel. So I'm left with 3 Mn plus 2 plus 2 PO4 minus 3 yields Mn3 PO4 2. For HC, still same idea. This time we have lead 2 nitrate with potassium bromide. So, and it says they're both solutions, so we know they're aqueous to start with. So PbNO32 plus KBr yields KNO3 and PbBr2. We're going to need coefficients here and here. They told us these ones were solutions, so they're aqueous. This one, potassium nitrate. I see potassium, alkali metal. I see nitrate, which are both qualifiers for aqueous. So I know that that one's a solid. So I'm going to break up all the aqueous ones. Pb plus 2 plus 2 nitrates plus 2 potassiums plus 2 bromides yields 2 potassiums and 2 nitrates and PbBr2. So nitrates are gone, potassiums are gone. We have Pb plus 2 plus 2 Br minus yields PbBr2. Remember when you get to this point in a problem to always double check your balancing on your net ionic, because if it's not right, then you've made a mistake and chances are there might be something really wrong. So definitely always look back. All right, for the last one, calcium nitrate and potassium fluoride. So they're going to make potassium nitrate and calcium fluoride. Coefficients are going to be a 2 and a 2. They told us these ones were aqueous because they said they were solutions. Potassium nitrate definitely is going to be aqueous, which means the other one is a solid. So we're going to have Ca plus 2 and 2 nitrates. We'll have 2 potassium ions and 2 fluorides. We'll have 2 potassiums and 2 nitrates. And then calcium fluoride I need to leave alone. Potassiums cancel, nitrates cancel. I get left with Ca plus 2 plus 2F minus yields CaF2. All right, number 9. We have 6.73 grams of sodium carbonate dissolved in enough water to make 250 milliliters of solution. What is the molar concentration of the sodium carbonate? So in order to get the molar concentration means molarity. So I need my 6.73 grams of Na2CO3 to be in moles. So I'm going to convert that one first. So mole-wise, I'm going to have 0.06349. I went a little crazy there with my unrounded. Oh well. And then molarity will be equal to moles over liters. And I know my moles. Here's where I regret writing all of those numbers. And then over the volume in liters, which is 0.25. If I divide that, I get 0.254 molar Na2CO3. So that's the first part of the question. Then it asks me, what are the concentrations of the ions? So you know Na2CO3 breaks up into 2 Na pluses and 1 CO3 minus 2. Oops. So if this is 0.254, for every 1 Na2CO3, we get 2 Na pluses. So it's going to be twice as much for the Na plus. So this concentration will be 0.058. And then this one is a 1-to-1 ratio, so it'll be 0.254. Okay, number 10 wants us to find the volume when given grams and molarity. So you know that ultimately we're going to be using molarity equals moles over liters. And you know we're going to solve for this liter value. And you know that we have been given this molarity, which means we're missing moles. So if we have 442 grams of KMNO4, I can convert that into moles. For every 1 mole of KMNO4, the molar mass is 158.0 grams. So that's going to be 2.797468 moles of KMNO4. So I'm going to plug in, bring this down here, I'm going to plug in my molarity, which is 5.80, and I'm going to plug in my moles, and I'm going to put my volume on the bottom, and I'm going to cross multiply carefully because people have messed this one up all the time, and you should end up with a liter value of 0.482 liters. Double check and make sure it asked for just volume. Yep, I was looking to make sure because a lot of times they'll say what is a milliliter, so I want to make sure my answer is expressed correctly. Okay, ion concentration problems. Okay, so the first one gives us Na2SO4, and they tell us the concentration is 0.258 molar. So that breaks up into 2 Na pluses and an SO4 minus 2. So the ratios are 1 to 2 for the first ion and then 1 to 1 for the second ion. So therefore this concentration is going to be 0.516 and this one is going to be 0.258. Those are your answers for A. For B, we have K2CR2O7, and they tell us its concentration is 0.124 molar. So again, it's going to break to its ions, so 2 K pluses and 1 dichromate. So the ratio, 1 to 2 and then 1 to 1. So this one's going to be 0.248, and this one's going to be 0.124. Remember, what's on the left side and on the right side does not equal. Okay, it has to do with the ratios. So the last one is BaCl2. It's going to break up into Ba plus 2 and 2 Cl minuses. So if this is 0.43 molar, then this is 0.43 molar. So the ratio is 1 to 1. And this is 0.86 molar. Let's see if I can squeeze 12 in on this page. So number 12 is the only time you want to be using MCVC equals MDVD. Do not use the dilution equation on a titration problem. I will mark all of your points off, and I don't want to, but I will. The reason why I know that this is not an actual chemical reaction is the concentration. The only thing changing, it's still the same substance. So we're going to be using MCVC equals MDVD. I apologize for my voice. I'm not quite sure what's happening to it, but hopefully it holds out. So it told us that the concentrated, ooh, that's wrong. Put that on the wrong side. Okay, hold on, start over again. So the concentrated molarity for this problem is 12 molar, and it's asking us to calculate how much we need. So we need VC, and then the diluted molarity is 0.25, and we have how much of it that we want? 500 milliliters. Notice I left it in milliliters. I could convert it to liters if I want. I just know that if I leave it in milliliters, then this VC I'm going to calculate will also be in milliliters. So when you get your VC and you round to 2 sig figs, you get the answer of 10 milliliters. That's 10 milliliters of 12 molar HCl. That's what that number represents. So it asks us to explain the process. So the process is get a 500 milliliter volumetric flask, fill it halfway with distilled water. Remember, this one we're going to fill halfway first. Then add 10 milliliters of 12 molar hydrochloric acid, filled very close to the fill line with distilled water, but putting the last few drops in using a pipette to get a perfect meniscus of the fill line, cap, and invert. Okay, this is a titration problem for number 13 because you notice you have HNO3 reacting with BaOH2. So acid-base reaction. Do not use the dilution equation. The dilution equation sometimes will make it seem like it's the right thing to do, but regardless, it is not. If you use it on a problem and it happens to work out, I'm going to mark all your points off because it's not an appropriate equation to be using. This is not a dilution. So what we have to do is just a little bit of stoichiometry. The first thing I always do is start by writing down what they've told us. They've told us we have 2.5 grams of barium hydroxide. They've told us that the molarity of the HNO3 is 0.345 molar, and they want us to figure out the volume that's related to the HNO3 for this titration. So always start with the one that you can find the moles of, which in this case is going to be the BaOH2. So I'm going to take 2.5 grams of BaOH2, and I'm going to convert that into moles to start with. So the molar mass is 171.3 grams BaOH2 for every 1 mole of BaOH2. And then I'm going to convert that from moles of BaOH2 into moles of HNO3. So for every 1 mole of BaOH2, I'm going to have 2 moles of HNO3. Make sure you balance that equation. And when I calculate that out, I'm going to find out that I have 0.02918, what will go to 86 moles of HNO3. Then I'm going to use the molarity equation. I already know the molarity of my acid is 0.345. I'm going to plug in my moles of my acid that I just found. And I'm going to solve for volume. So my volume is going to be rounded to 3 sig figs, 0.0846 liters. The problem said, what is it in milliliters? So 1, 2, 3 places to the right, and I get an answer of 84.6 milliliters. The next one's a titration problem too. Again, notice acid reacting with base. As soon as you see that, you know that you are dealing with a titration problem. And the first thing you want to do with a titration problem is to get a good working balanced equation. So our equation is acetic acid reacting with sodium hydroxide. And it's going to make sodium acetate, our salt, and water. Nice easy one with balancing. It's already balanced. We know we have 25 milliliters of this. We know we use 32.34 milliliters of this, and that its concentration was 0.897 molar. Here's your starting point, because you're trying to find this concentration. So I'm going to start with NaOH, and I'm going to use the molarity equation. Molarity equals moles over liters. I know my molarity is 0.897. I don't know the moles, but I do know the volume. I do need to put it in liters though, so you notice I moved my decimal. So when I calculate that, cross multiply that, I end up finding out that I have I feel like I may have over-rounded this, but I don't have a calculator to check my work with. I may have over-rounded right here. If I did, please make sure that you left yours more unrounded. We usually go 2 past how many sig figs we're going to have in the end. Okay, so now I'm going to take that mole value, which is of NaOH, and I'm going to convert it into moles of my acid. The ratio is 1 to 1, but we do still need to show that step. So for every 1 mole of NaOH, I have 1 mole of acetic acid. And it gives us 0.0290 moles of acetic acid. Now that's not what we wanted. We wanted molarity. So molarity equals moles over liters. My mole value, again, you may have a better number than that because I still feel like I didn't leave that unrounded. And then over the volume, they told me the volume was 25 milliliters, so I converted that into liters. And I'm going to solve with 3 sig figs for a molarity of my acetic acid to be 1.16 molar. All right, for number 15, explain the process of a titration experiment. So you just want to know the basics, you know, that the base goes in the burette, the acid goes in the flask. Don't forget the indicator in the flask. Making sure you're washing down the sides of the flask. You can go fast at first, but make sure you're slowing down when you get close to the equivalence point and end point, the color change. Make sure that you use proper procedures to rinse out your burette ahead of time to make sure it's clean. All those little details. We did it in lab. I think that you really probably have a strong understanding of what's necessary because of what we did in lab. If you were to be asked a question like this on the test, don't worry about the pH meter discussion part of it. You don't need to include that. Questions like this are meant to more talk about the burette titrations, more so than anything else. Okay. For number 16, though, back to some math. They want the mass of strontium chloride needed to react with 100 milliliters of AgNO3. So since they're talking about a reaction, you know you have to write a balanced equation. If you try to do this without a balanced equation, things will not go well for you. So please make sure you do. So here is the balanced equation. Double check yours. If you have an error, it's, you know, a chance that it's in your balanced equation. They want us to find grams of this, where we know how many milliliters and molarity of silver nitrate we have. So I'm going to start here. Always start away from where you're ultimately going. So I'm going to use my molarity equation. Oops. Don't know what that part's for. So 0.2 molar, and I don't know my moles, but I do know my volume. Put it into liters, and that tells me that I have 0.02 moles of AgNO3. And then I can convert from moles of AgNO3 into moles of SrCl2. Oh, you know what? Let's do another conversion because we don't want moles of SrCl2. We want grams. So I can just add it on there, tack it on. Molar mass is 158.6 for every 1 mole. And I'm going to round my final answer to 2 sig figs, so I get 1.6 grams. All right, number 17, looking at that graph, it says use the graph to the right. Do you think this was the reaction of a strong acid and strong base or a weak acid and strong base? Give 2 reasons. You should have said it was a weak acid and a strong base. One reason is the pH at the equivalence point. So halfway up that jump is at 8.62. That's basic at the equivalence point. So therefore, it had to have had a stronger base than acid. The second reason is notice how high the pH starts. On the y-axis of the graph, the pH started at 3. Strong acids typically will be under 2 for a pH, so that's another indication. Number 18, they wanted you to figure out what the pHs were at the equivalence point. So find halfway up the jump. Of course, it's an estimation depending on how good or bad of a graph I show you. For number 18, I would say the pH at the equivalence point was 8 for that first one. And for the second one, I would say the pH was around, at the equivalence point, was around 10. And if you had, 9.5 to 10.5, that would probably be just fine. All right, so make sure you take the time to study all of this. Come in, ask questions, email me if you're studying over the weekend or something. Just make sure that you are well prepared for your test. Remember, if you get less than an 80, you're going to have to come in anyway. So do the prep work on the front end. All right, good luck, and let me know what I can do to help.